The three types of cues that we'll talk about today that the brain uses for depth perception are binocular cues, meaning they involve both eyes, monocular cues, which are only involving one eye, and motion cues, which ultimately involve some kind of motion. Starting with binocular cues, this works on something called binocular disparity, and this refers to the fact that both of our eyes and thus the retinal images are slightly different in what they see the world because they're located in different places in space, even though they're very close together. It's illustrated well in this image here, where you can see that these two dots that are being looked at by the eyes, even though dot A is super close to this person's nose, but I guess it does look a little cross-eyed. Never mind. Here you can see that as the left eye is viewing, its dot, the A and the square B are very close together, while the right eye is looking at the same two images, but the image cast on the retina is a little bit different. Now the brain is able to compare the difference between these two images and use this as a way to evaluate the distance, both A and B in this case would be, from the person, or from the eyes ultimately. It turns out that if you can rig up a contraption by which you can show separate images to both of your eyes, and you show them images like are presented here with the dot square and the dot square, it will actually give you the illusion of those two items being certain distances away. It is pretty hard to do without a contraption that can isolate what each eye is seeing though. Moving on to monocular cues, these, just like the name suggests, rely only on one eye. The first is for eye muscle sensations. These are referring to the muscles around the lens in the eye, and as they relax or contract, adjusting how thick or thin that lens is, allowing it to focus light onto the fovea, it can use information about how much the muscles are engaged to give an estimate of how far away the object is that is being focused onto the retina. Again, this only works for a certain distance away, because after a certain point, there's not much adjustment that will take place in the lens anymore once you go beyond a certain set distance all the way out to the horizon. I forgot to mention this on the last slide, but this is true for binocular cues as well. The images cast on the retina are really only different for things that are roughly close to us. Once you get beyond a certain distance, I'm not 100% what that is. My guess is it's going to not be more, or probably around like 100 feet maybe. But again, please don't quote me on this because I'm not sure of the exact number. But beyond a certain distance, there's not going to be really any discernible difference on the images cast on both retinas, and therefore it becomes very difficult to gauge distance beyond certain distances. The next type of cues are called pictorial cues, and these actually have two different parts. The first is referred to as interpolation, and this just refers to the inference that one thing is farther away than a second if the second one blocks the view of the first. And not entirely, because then of course we wouldn't know it was there, but it blocks it in some partial way. And then remember when we talked about the Gestalt theorists and the organization about how our visual system works, we tend not to think that thing just ends there, but continues behind this other object that is blocking our way. And thus, this combination allows us an additional inference that the object blocked from view is further away than the object that is blocking it from view. Another is the size cast on the retina. Now, here, just as you would in a little picture, if you were drawing humans who were close and far, you would draw them at different sizes to illustrate how far away they were. In the same way, your brain is able to use the images cast on the retina itself and the size of them to estimate yet again how far away certain objects are. Finally, in monocular cues, are called texture gradients, and this refers to the idea that if there is some type of uniform or textured uniform pattern, that we can use that pattern and how it changes over distance to estimate how far away something is. A common example of this is when you look at railroad tracks. If you sort of stand, well, don't stand directly on railroad tracks, please. If you look at them though, you will see that they often tend to converge out into the distance. This is because you're ultimately having a smaller and smaller retinal image that is cast on the retina the further you look down these railroad tracks. And this is what gives that illusion of them coming together. This is also why artists are able to use perspective in an artistic sense to give the illusion of depth, because those two little lines coming slightly close together ultimately reduces how far apart they are on the retinal image, and this tricks the brain into perceiving it as depth. Finally, there are motion cues. Here, the first is referred to as motion parallax, and this is talking about the speed at which an image moves across the retina. Now, the way this works is that objects that are close to us will tend to move across the retina very quickly, whereas things that are far away will tend to move much slower. A good example of this would be planes. If you were standing, hopefully not too close to a runway because they're super loud, but you watch them taking off, they move quite quickly. But when you look up into the sky, it takes them a long time to move. And now imagine yourself also in that situation, except you had to keep your head stationary. When you watch the plane take off, it would literally enter your visual field and then exit your visual field in almost no time at all. Whereas when you look up at the sky, it takes a little while for the plane to travel all the way across your visual field. This is a way that your brain will also use to estimate how far or close something is based on the speed at which it is moving across your retinal image, or retina, I guess. The last is changes in the entire retinal scene, and so this is oftentimes referred to as optic flow. And what they're talking about here is that when we ourselves move, our entire retina perceives an entirely different image because of our new position in space, and thus our perspective itself has changed. Now, when you move closer to something, that thing casts a larger and larger image onto the retina, and this increase in collaboration with the speed that we're moving is used to estimate how far away an object is. So if we're moving at a constant speed and one object is growing much faster than the one that is growing faster is much closer to us. Finally, redundancy. So like previously mentioned, all of these systems are running simultaneously and in parallel. It is not one before the others, and pretty much the only time these will turn off is if there is some type of damage or if you close one eye in the case of binocular cues. Now, while it might seem strange that the brain has devoted so many resources to so many different mechanisms to all provide ultimately the same information, in many ways, yes, that can be confusing because it isn't how we as human beings generally build things. If anything, people like NASA have maybe 3 fail-safes about something, but most of us, when we make our plans, don't even consider the fact that they could go wrong. And here you have many, many systems all ultimately running simultaneously. One, this lets you make up for in case you lose the ability to use one or more of these. For example, let's say, hoping it never happens, one loses function in one eye. It would be pretty bad if the only way we had to gauge cues was through binocular cues. Otherwise, it also allows it to make up for any loss in function that one may have. Some of these are limited by distance, whereas others are more flexible in how far away we can gauge things as distance relative to others. So having multiple ways in which to gauge depth is just an adaptive way, and it allows us to operate in a very flexible manner when we're dealing with the sort of chaotic nature of the world. And at the end of the day, perceiving depth is something that is fundamental and vital to an organism's survival, especially one that locomotes. Now, imagine just how hard it would be for you to get a snack if you could not accurately gauge distance. Further, our ancestors would probably have never survived lions. On that one last final note, you will see this theme over and over. There are many situations in which the brain has a large degree of redundancy. And again, mostly just in case. And chances are those things weren't built into it, but the ones that spent the extra calories on those redundant systems are the ones that survived the longest.